will be recorded, and if you would like to show your face on Zoom, please turn off your video. Or if you don't want to be recorded, there's still time to leave the seminar now. Welcome and thanks for joining us today. For those of you who don't know me, I'm Rob Raven, Deputy Director of the Monash Sustainable Development Institute and also Professor of Sustainability Transitions. And today I'm joined by Jeff Webb, the Research Director of Monash Data Futures Institute, who's currently on leave and joining us from beautiful Morning Peninsula. And we will be your hosts and moderators for today. Before we start, I wish to acknowledge the traditional owners on whose lands we are gathered, physically dispersed and virtually constructed. I pay my respect to the elders past and present. So welcome to the first of what we hope will be many seminars jointly organized by the Monash Data Futures Institute as well as the Monash Sustainable Development Institute. For MSDI, sustainable development is the core focus, and in alignment with UN missions and developments, we also investigate the role that artificial intelligence can play as a means to that end. And AI, of course, is a key focus of the Monash Data Futures Institute, and its application to sustainable development is one of the priorities in MDFI. So this collaboration and this seminar is a good example of that collaboration, comes quite natural, and we expect on growing that collaboration. Today we have Dr. Alex Helf. Alex is the Research Director of the Center for Observation Program in CSIRO's Astronomy and Space Science Unit, and also an Associate Professor at the Australian National University. And he has over 25 years experience in terrestrial remote sensing and has led several projects and research teams since then. His PhD is from the University of California, Davis, in the area of plant physiology. And Alex has focused his work on designing ways of better use of satellite Earth observation data in forestry, agriculture, disasters, and ecosystem science. And he also represents CSIRO at the Interagency Committee on Earth Observation Satellites that is designing future Earth observation data architectures for global Earth observation programs, as well as promoting the use of this data for achieving sustainable development goals. So I think, Alex, as I said before, I think you are the perfect candidate for this first joint seminar.
Thanks.
Just a few, no, thank you, I should say. And before I hand over to you, Alex, maybe just a few housekeeping rules for everyone. Please keep yourself on mute unless you're presenting. And you can use the chat function if you wish to express comments or questions during the presentation. After the presentation, we will have time for Q&A, and we will do so either by, you can raise the hand function, or you can ask a question in the chat, but also there's a possibility just to unmute yourself and I will give you the room to ask your question yourself. So over to you, Alex.
Thanks very much, Rob, and thanks again for the invitation. And hello, everyone. I'm speaking to you from Ngunnawal country here in the ACT, and hopefully my presentation will be of interest. I will start sharing my slides. Just give me a sec. So hopefully, please confirm if you can see that.
Yeah, perfect.
All right, thanks very much. Yes, hello, and again, I'd like to just thank you again for the invitation. And I know we're having to do this by video, but hopefully it's of interest and we can interact as much as we can. Stop me anytime if there's anything burning that you'd like to ask before I continue. So what I want to talk a bit more about is some of the work we're doing in CSIRO, but also some of the collaborations we have with international agencies around the world that are interested on the interface between sort of big data, Earth observation, as well as how we can make this data more accessible and useful for those countries who are trying to report against sustainable development and specific sustainable development goals that the UN has set up that countries can then report against. So I'll touch on a few of these things. I'll also finish towards the end to talk a little bit about a specific project I am looking after at the moment here in CSRO, which is the AquaWatch mission, which is one that we're just starting, but I think that might be of quite a bit of interest to many of you, and specifically because we're also quite interested in building partnerships around this mission. It's not just a CSRO mission, it's really a national partnership. I'll give you a bit more detail at the end. Just a bit more about CSRO and specifically the center that I lead, Center for Earth Observation. So we've been in operation for a couple of years, 3 years now, and it's really about supporting our scientists internally within CSRO that have been using remote sensing and Earth observation data now for, as you can see, almost 75 years since the launch of some of the first Earth observing satellites from the US that we had access to. And we have about 80 scientists across the different parts of CSRO using the data to develop different applications in agriculture, in mineral exploration, in water quality, and ocean monitoring, and things like that. So the center was really set up as a cross-organizational unit that allows our scientists to come together virtually or physically a couple times a year to share experiences, share tools, and share interesting opportunities that they might work together. We also have a mandate to work closely with the Earth observation industry, as well as other fellow government agencies such as Geoscience Australia, the Bureau of Meteorology, and now, of course, the new space agency. As of late 2017, we also took we co-invested in basically getting access to the tasking of a small UK satellite called Novasar. Some of you may have seen some news last week about the fact that we have now set this up as a national research facility, which allows people to access the tasking capability of the satellite and point the satellite at areas of research that you might be interested in. The data will then be collected, downlinked straight into an Australian receiving station, and then made available to you for research purposes. So it's a research facility. It's not a big mapping mission for operational purposes or commercial exploitation in some respect. It's mostly a research facility. So we have a team that's tasking that satellite there, and it has quite a bit of interesting technology on board, and I'm happy to sort of cover that a bit later on. We're also working a little bit on how to make the processing of the satellite data more effective, both on the satellite itself before it gets downlinked, or once it's downlinked, how to then make the data more efficient and how to process it in a more efficient way. As part of this, traditionally, we have also been representing CSRO and both also Australia internationally at forums and committees that have to deal with Earth observation and societal benefit derived from Earth observation. So there is a lot of data already being produced. Some of you may have been using some of these satellites already from the US, from NASA, or NOAA, the meteorological agency, or from Europe, different Sentinel satellites from the Copernicus program, or from Japan and things like that. So a lot of this data is freely accessible, open source, openly available. In some cases, you need to have friends in these agencies to get you access if they're pretty experimental data sets. In some cases, you need to just find your way back to these data sources or the data archives to find the data. But at the end of the day, it's just a deluge of data that we can access. As I said, there are 150 satellites potentially available for us to do research in, and each of the satellites have one or more sensors on board. So there's quite a few sensors measuring different aspects of their system that are available to us. I'll share this slide deck with you, but you can also follow this link that I show you there. It has it's like a compendium that's produced every year or couple of years with all the satellite missions that are already in space, and an update on these, or those who are being planned to be launched in the near future. So it's a fantastic resource if you're interested in a certain variable or a certain type of data that you're interested in for your research. This is just one agency. This is the NASA mission that has a huge number of satellites already in space from NASA. NASA tends to be the science agency. It's a science mission agency, not, let's say, an operational satellite mission agency. They do, however, build satellites and certain technologies that are then operated operationally on a routine basis, like you have for the Landsat satellites, which are sort of the workhorses of the US. Hang on, I just lost my here. And so in some cases, NASA just builds the satellite, but then hands it over to these operational agencies to then operate on a routine basis. Well, there's a huge number of technologies that are still to be launched and will be launched in the future, all about Earth observation. Different variables and different data streams coming at us pretty much, and available to anybody in Australia if we're interested in. So part of the challenge, of course, has to be in that we have different government agencies around Australia, state and federal, who are using all this data for mapping purposes, and partly the challenge of this is that we have so much data that it had become a big problem of having multiple copies of the same data set, different levels of processing, all hosted by different agencies around the country. So we set up a few years back what's now called the Regional Copernicus Data Hub, which was originally designed to bring in data from all the 6 Copernicus satellite generations from the European Space Agency under the Copernicus program. And each of the satellites has at least one, if not more, 2 or 3 satellites of the same type going around Earth, collecting data. So there's a huge amount of data, and we set up this Copernicus Data Hub amongst all these agencies, federal and state, to then provide access to in a single location where we can curate and manage the data in a consistent way, make it freely available to anybody, do a lot of quality control checking, and basically it's collecting data for this part of the world that is surrounding Australia. So it's a big part of the globe, because as you know, as you can imagine, I mean, Australia's exclusive economic zone and the areas we look after almost cover 1/8 of the globe already. So collecting data from all these different 6 satellites, and there are multiple generations of each, is a huge data archive that we're just building up at the moment. As every data set is collected, we pull that data through data networks from Europe straight into the data hub that's managed by Geoscience Australia, and currently sits on the National Computation Infrastructure System here in Canberra at the ANU. But you can go and access the archive. You can access and download data using some of these this web connection. We ultimately want to also make available some sort of pre-processed data so that it's easier for those who are not interested really in doing the, let's say, the atmospheric correction or some of the geocorrection of the data, but just want what we call analysis ready data straight for use into developing specific applications that you might be interested in. So there's quite a bit of infrastructure sitting behind this that is eventually going to make the data a lot more accessible, not just to those of us doing the science with relatively raw data, but those who are more interested in using the data to a common agreed standard that people might be interested in using for sort of routine use, and they're happy with that level of standardization for their application. But this is the problem. We're now collecting so much data and archiving it because our scientists want to know, not only get the latest image of some area of interest, but they want to get the whole history of what happened to that piece of land or that paddock or that coastal area over the last 30, 40 years. So it's building up quite rapidly, and this sources and variety to this data set. Just incidentally, this blue wedge, the biggest one, is the Himawari geostationary satellite from Japan, which is basically producing much of the data that our Bureau of Meteorology, for instance, uses for some of their weather forecasts. Now we're also collecting and archiving that data, which is some of you might know it's actually collected every 10 minutes over the whole disk that covers basically that image I had on my first slide covers all of Australia all the way up to Japan and so forth. So it's a massive data set, again every 10 minutes collected, and it's a fantastic data set for lots of really interesting applications, but it's big. And so we've been working with not just internally within CSIRO, but with our fellow agencies, including Geoscience Australia, on how to develop a system where you can bring all these different data sets together under a single platform in an analysis-ready format, let's say, that everybody can access quite easily and use in a consistent way when you want to maybe work with different types of technologies, different sensors. And as many of you know, of course, in this line of work that you do, it's the trend globally is more and more, of course, free and open data. The computing technology is advancing quite a lot, especially cloud computing is now becoming very commonplace. We're moving for some of these applications completely away from big supercomputers to doing everything on the cloud. And the open source software community has also been very, very active, and more we're using open source software tools rather than commercial off-the-shelf software. So I guess our solution is what some of you may have heard about, called the Open Data Cube technology, again, developed in Australia. So we're quite proud of that. And it's all about bringing time series of data, satellite data, into a single place, so that, and it's all pre-processed, atmospherically corrected, spatially aligned, so that for 1 pixel of land, your farm, let's say, you can drill through the whole time series in a consistent way and look at how that piece of land has changed over the last 30, 40 years, depending on the length of the archive we have for that that specific sensor. And I think the longest archive we have is for the Landsat generation of sensors. It goes back all the way to probably the late 70s, early 80s. So it's a fantastic historical data set for all sorts of really interesting applications. And I'll show you some examples in a minute. But again, the other key element here is that the data is being pre-processed to a reasonably good published standard of processing of atmospheric correction and geocorrection, so that you can stack these images up quite nicely, and you get an image which is an image of reflectance of the land, so you don't have to deal with any of the atmospheric issues or cloud cover issues and things like that. We've also chosen to write this all in open source, mostly Python code, so that anybody around the world can access the code and set it up for their country if they're interested in, for instance. And so again, there's some links there that you can go and see for yourself, and maybe even download some of the data, the software of GitHub and put it on your system if you're interested in. So it's really changing a massive paradigm that many of us in this area have been dealing with, where you have a number of a user that's very interested in a specific data set or a specific application, going to the original catalog of the US or Europe or something, and then dragging the data across, pre-processing in some way, then creating the map product that user is interested in. And the second user have to basically do exactly the same, sometimes exactly the same data set. So what we're trying to do with the data cube is that we have a single data set that's processed only once, where we have different types of satellites and sensors in the same environment, in the same platform, and then different people can just go to the central cube, let's say, and use the data for different purposes without having to go through 60-70% of the effort, which is cleaning up the data most of the time. This is a quick example, hopefully you can see it, is of one of the early applications where we map basically the whole continent using Landsat data and stack the data, the different images for each part of the country, and did quite a bit of cloud screening and pre-processing, and basically processed the whole country. In this case, it was in sort of tile form, and created a map. In this case, it's a map of the presence or absence of standing water. I think the different colors basically show you the frequency of how much that pixel had a signature for water present, and it's become one of the main data layers that now agencies such as Geoscience Australia produce on a regular basis through some of their projects called water observations from space, and also Digital Earth Australia. So it's been a major achievement, and to be able to produce that product alone at 25-meter resolution across the whole continent took a lot of processing, as you can see there. Something that doing it the old way would have taken years and years to process, because it's quite manual and quite laborious. It just took 3 hours in this case a few years back on the NCI supercomputer. Here's another example where you zoom into a little piece of land. In this case, it's an area, I think, in New South Wales, where a new mining operation is getting in, and you can see the progression of the land clearing there and the development of the mine, and making sure that the mine stays within the allowed lease and the boundaries that it was given. So it's a very simple analysis. In this case, you can see the odd clouds still not being filtered out very well, but it's a fantastic tool also for policy makers to really make sure that some of these operators stay within what they agreed to do inside those boundaries that they're developing the mine. So it's really about stacking images, taking out a lot of the artifacts, cleaning it up, which at the end makes it quite a nice compressed way of compressing the data already, that you would otherwise have to read off a big disk or a bunch of magnetic tapes. And what we've done is set up this as what's called the Open Data Cube infrastructure, with a bunch of APIs, where the data is indexed quite carefully, pre-processed, as I said there, and then anybody can come and develop their own tools and applications on top of that piece of infrastructure, all as Python libraries and things like that. So I guess I covered a lot of this, but it has made it so much more efficient for many countries and others and partners around the world to use this approach. And the applications suddenly become much bigger, much more powerful. You can suddenly map your whole country if you're interested in, or your farm. It doesn't matter. And it's making use of especially cloud computing infrastructure and efficiencies there. It reduces the cost to governments already of having to invest in massive computer infrastructure if they do a lot of this processing in a smart way on the cloud. And so again, it's basically what I mentioned before. It's a bunch of Python, and we're using Jupyter notebooks for training and for tests and for development of new algorithms. We now will have lots of sensors and different data sets on the same platform. We're not treating satellite images as images or scenes anymore, but it's just a bunch of pixels that have their own index, and the system will just find those pixels when it needs it for processing. I'm not going to go into very deep architecture because that's not really my field, but as you can see there, I mean, we're using Amazon as a commercial cloud provider for some of the work we're doing in CSRO. So we developed an Open Data Cube version or instance we call EASY, Earth Analytics, Science and Innovation, which is a fantastic tool that our scientists, more than 100 scientists, are now starting to use in CSRO to develop algorithms to test big processing jobs that they need for using Earth observation data. And we're using some of the new approaches in efficient memory management on cloud and things like that, as well as using the spot market to reduce the cost of running the cloud in some cases. Many of you probably know this much more than I in terms of the language and the tools that we're using, but there's quite a few layers of administrative control we have over the EASY Data Cube now. We can also monitor individual users as they use the system, and therefore we can either charge their project specifically for the use of that amount of resource from, let's say, the Amazon cloud, without having to then impact anybody else's project, which is a great way of managing it. Similarly, if a private company or small startup wants to come to the cloud, to the data cube, can also use it either with existing tools that are already sitting there or with applications and algorithms that they might want to develop themselves. And we have a way of eventually charging them just for the use of that time and that capacity. And then they move out and finish the project and don't have to think about investing in massive infrastructure themselves if they want to run big projects like continental type maps and things like that. The beauty of this now is that a lot of the big space agencies are now putting all their archives on the cloud as well. So we're tapping into Amazon archives, that are managing the full global archive for the Landsat satellites, for instance, from the US. It's all sitting on an Amazon West system in the US. And we're also now starting to tap into the same sort of cloud-based system that now is holding a lot of the European Copernicus data sets. So in some respects, we don't need to have a copy of the data anymore ourselves. So the system will know where to find the data and just process the data it needs for that specific application. That's subject a little bit to bandwidth and data transfer costs and rates. In some cases, when we have projects for a specific country, we might need to make a copy of that country's data set just to be able to run more efficiently. But in theory, we wouldn't have to go to set up our own archive because we know, and the data is well curated in other cloud infrastructure around the world. It's written so that eventually you don't just need to have a cloud or a supercomputer. You can also set it up on your own laptop and do some for research purposes. It can run a very small piece and smaller data sets, and it doesn't matter. It's all cloud-based, Python-based language that you can set up quite easily. It's beyond Australia, this has become extremely popular now. We now work, and other adopters of the Open Data Cube philosophy come from the US, a number of, as you can see, NASA, the US Geological Survey agencies around the world, in Vietnam, in Colombia, in the UK, Swiss Data Cube, lots of different countries are now adopting that. And this is sort of a map of all the different data cubes that are either operational, under development, or those countries that have come to us or Geoscience Australia to help them set up their own data cubes, because they have the same pain we have of managing these big data sets in a consistent way. So some early applications, as I very quickly go through these, because I think I might be running out of time, are in remote sensing world. I think these are a number of different ways of processing the data and different indices people use for different mapping applications, for both land-based applications, mapping forests, looking at water bodies, and I'll show you some more examples, or land use and land use change, deforestation, and things like that. Typical applications that we see popping up around the world are, as you can see, this long list of things people are using data cubes for now. And many of these applications will eventually also be used more and more as a way for countries when they don't have enough ground data and they have to rely on satellite imagery to then report against certain progress against the Sustainable Development Goals. We have a very large project, mostly run through Geoscience Australia, for basically developing a massive data cube for Africa, which is called Digital Earth Africa now. And it attracted quite a bit of funding from philanthropic organizations as well as the Australian government to set that up. And if you're interested, they have their own website, their own Twitter feed and everything, and it's making some fantastic progress and training a lot of people in Africa who never could dream that they had access to so much data for their own country or their own region through a platform like this. So it's become quite a nice project. Again, some examples from some of this work. This is a flood and water mapping project where, again, the different colors show you roughly the how many observations, how many pixels were identified over time between, in this case, 2000, 2017, that had water in it. So it's basically a way to visualize how this specific lake in Kenya is basically running out of water because it's either extracted, too much water is being extracted relative to what's coming in, or just massive drought or climate change impacts there. Again, the power of a very simple algorithm, but a fantastic big data set sitting behind it and nicely curated and processed so that you can do these sort of analysis quite easily. Again, this is a water quality indicator. Again, it's another Sustainable Development Goal indicator. In this case, it's turbidity, looking at water turbidity over time for different snapshots of time. Again, all nicely laid on top of each other, so you can do quite nice comparative studies. In this case, I think it's a coastal erosion or growth area, so that you can really look at how coastal areas have changed or eroded over time. Again, another SDG goal as UN SDG indicator on urbanization. Again, usually these are very simple algorithms, but they are applied to these big time series that allow you to visualize things quite easily in terms of how has this part of Kenya grown in Nairobi, the city of Nairobi. Forest and deforestation is a typical and very common application that many countries are following. Again, big value of the data cube, partly because in some of these places there is not too many chances to get a cloud-free image of these areas, especially in the tropics. And what the data cube tends to do is basically looks for the clear pixels and just creates these mosaics out of whatever good pixels it can find in this archive. And if you have enough images to basically do a time series, then you can do quite interesting data analysis of that. But I mean, we can take images that only have 10% of the image it's good, and we don't have to throw it away just because there's 90% of the pixels are cloud affected. It just picks the good pixels and keeps that in their archive. Mangrove mapping, how the mangroves have developed, is another one, which is quite a common application. Blue carbon, sea level rise, all sorts of impacts on mangroves. Again, crop mapping around the world is now starting to use this sort of technology, looking at how are cropping areas behaving this year relative to the historical mean, for instance. Big organizations like the FAO and others are using some of this data to predict what next season might be, or whether there's going to be a famine in this part of the world or that part of the world in terms of production of food. And that's a really powerful technique, using relatively simple remote sensing data analysis algorithms. So what we've been doing with our fellow agencies around the world, the space agencies, looking at which are the SDGs, Sustainable Development Goals, and their indicators that we think can be in some way quantified or mapped with satellite data. And I guess this table, and there's more information in that I can pass on to you, would show that quite a few of them is something that we can at least support with in some way using satellite data. Ideally, you want to, of course, back it up with ground measurements or census data, for instance, on population growth and things like that. But when there is no census and no other way of looking at changes in urbanization, then you saw an example of how we can use satellite data to look at the growth of cities and things like that. I just might spend very few minutes talking a bit more about this AquaWatch project that we're looking after here in CSIRO. It tends to also look at a number of variables, which we hope will also contribute to a number of the SDGs into the future. AquaWatch is really about measuring water quality and using a combination of in situ sensor networks and satellite imagery and modeling tools to then produce eventually a data product for Australia that will on a 24/7 basis provide information about the quality of drinking water inland, but also the quality of water around the coasts, to make sure that people are managing that very rare and valuable resource properly, or that, for instance, industries in the aquaculture industry, for instance, in the fish farming industry, can be warned before maybe some pollution or some toxic algae is heading their way so they can harvest the fish before it hits them. We want to set this up and hopefully by 2026 have an operational system that brings in all these different data streams, the in situ sensor network, which could be, imagine something like, I don't know, 5,000 or so instruments in the field in different parts of Australia, lakes, rivers, and coastal areas. And ideally all uplinking their data in real time, near real time to communication satellites or IoT satellites that would then eventually integrate this data in a single platform. We would then try to build and design custom satellites, hopefully built by the Australian industry in the next few years, that would then look at specific variables of water quality we're interested in mapping. So when you combine these two different data streams together, perhaps with some sort of forecasting modeling capability, we basically create a 24/7 data product that anybody, any manager around the country would be able to use to monitor water quality. At the moment, these are our partners in this AquaWatch partnership. Our biggest partner is the SmartSat CRC, a new CRC that got set up a year or two ago in Adelaide. But they're our bigger partners, and I think somehow I lost their logo, but they're one of our biggest partners in this AquaWatch project. I can't see Monash there, but the doors are very much open to also have you partner in this mission. I think it'll be fantastic if we can work on some sort of interesting project we can do together. As I said there, it's about trying to map water quality and maintain safe drinking water also for rural communities, but support again, and also I guess sustainable land management, so people can really look after whatever is causing water quality problems, and see if it's to do with land use or erosion problems or just lack of water that's just accumulating and building up toxic algae or something like that. On the coastal side, I guess there's lots of opportunities to use AquaWatch data in the future to support a lot of industries as well as tourism, and of course monitor the health of our reefs and seagrass beds and things like that over time. Harmful algae blooms. I just had this slide here, but basically shows that the presence of harmful algae blooms are having major impact all around the world, and that's just growing over time. So we think that AquaWatch having one or more satellites constantly orbiting Earth in low Earth orbit will potentially contribute to in some way to some of this big issue that's happening all around the world as well. And I think I did mention this. I mean, we're trying to not just have satellite imagery here, but integrate it with ground sensors that we want to roll out around the country. And combine it with some sort of modeling tools that can then give us a bit more of a predictive capability. So we can warn people ahead of time that there might be, for instance, a toxic blue-green algae bloom about to happen in a certain drinking water reservoir, and things like that.
Alex, just quickly noting we have about 15 minutes left.
Okay, cool. Thanks very much. I think I'm about to finish. So these are some of the products that we think we will produce. I mean, chlorophyll concentrations in water bodies, dissolved organic matter, cyanobacterial pigments, and total suspended matter are typical products that people in the water quality industry use. But we hope to, when we develop these new satellites, hopefully make these a bit more of a quantitative measurement, and measure these things on a routine basis. It will not only map water bodies and water quality, but we think we'll also map some really valuable sensitive ecosystems, like in this case, mangrove change over time. I think I better move on, and that's basically what we think will be the roadmap for the AquaWatch mission. We want to begin developing a concept of what the satellites look like, and we might launch some smaller CubeSats and sensors that we want to test beforehand, so that we're ready then to build the bigger, more operational satellites in the 26-28 timeframe. Alongside of that, we're setting up a bunch of local test places, test beds, and pilot sites where we are going to be testing some of the implementation of this technology. These are some of the test sites we're currently using at the moment. You can see there. We need one in Victoria, as you can see. We haven't quite gotten there yet. So I might just leave it there, I think, and finish there. Thanks very much.
Thank you very much, Alex. And maybe if I can ask you to stop sharing your screen
Yep.
so we can see each other a bit better. And then I'm happy to open up the floor for any questions or discussions or comments. Feel free to raise your hand with the function at the bottom of your screen and the reactions. Yep, I think Andrew, you have raised your hand, so please go ahead with your question.
Yeah, thanks, Rob. Hey, Alex, great presentation, and
Thank you very much.
Reassuring to see that CSIRO is still really at the leading edge of all this Earth observation work. Amazing. Hey, my question relates to this idea of processing images, because I understand, or I gather, that a lot of Earth observation images, the raw satellite data still being processed on Earth. I guess my question relates to how close are we to satellites actually, or for there to be space-borne infrastructure that can actually undertake a lot of this processing in real time on board, so as to, I guess, improve affordability, flexibility, and ease of development for a lot of people who are using these Earth observation images?
I think we're getting very close. There are a number of, let's say, experimental projects underway. In CSIRO, we have a project with a certain big aerospace company where we are testing onboard processing and creating some of these maps I showed you on board the satellite. So that means you have to basically do all the corrections in space of the imagery as it's been collected, and then do the application to the algorithm. So there's quite a bit of work happening. The European Space Agency, I think, launched a small sat or a CubeSat not that long ago that has a specific AI capabilities on board the satellite. Nothing is sort of being done operationally. Let's say the big satellites, the weather satellites, are not doing that. I guess people still rather downlink everything they can and then clean it up afterwards. But
yeah.
I think for very quick turnaround applications, I think you'll see more and more of those being done in space. And even cloud computing in space is now starting to become a bit of a buzzword at the moment.
Thank you.
So it's moving quickly.
Thank you, Andrew, for that question. We got another question from Mitzi. Maybe show yourself.
Make myself visible. Thanks very much for a great presentation, Alex. I guess I have a less technical question, maybe representing some of the MSDI-minded folks. But I guess I'm interested to know how people that are interested in using or translating some of the information that's coming out of AquaWatch, to say policymakers in the community, might get involved, or if that's something that you and the SmartSat team are already doing.
Well, I think we've spent only 1 year so far since we started this project, and mostly doing a lot of consultation work, understanding how people are currently doing water quality assessment across Australia. Are they just throwing a bucket in and then picking up the water and taking it to the lab? Or are they using sensors here and there? Where are the gaps? How quickly do they want the data on their smartphone? And how does it need to be presented? So we're just going through all that process as part of the design of the mission. So we haven't solved all these problems yet, but I can show you a very, very long list of potential users of this, because all the way from water utilities who are interested in drinking water, making sure it's clean and safe after a bushfire, for instance, to desalination plants who are interested in making sure that they don't suck in anything that just clogs up their filters, aquaculture industry and drinking water. So it's huge spectrum of users. So we're trying to balance what they all want and where the gaps are with what the engineers think they can build, I guess. It's a bit of a trade-off exercise, which we're going through. But,
I guess if I can be sneaky then with a quick follow-up question, there's that pull from them as well. It's not simply you going and saying, look, here's the potential, this is what we can show you, but they're actually seeing that potential themselves.
yeah, we put in the user consultation front end in this project rather than a technology push. It has a bit of technology push because we're nerds and we like that, but I think the user consultation has become really, really important for us. Yeah.
Thanks.
Thank you, Mitzi. And maybe while we're waiting for someone else to raise a question or comment, I wanted to ask you, Alex, what are the potential, are there any potential risks of misuse of this kind of data, given that you can peek across borders in quite a lot of detail? Did you come across anything like this? How are you taking that into account in designing these systems, or even letting it inform who you are collaborating with and with whom you're not collaborating?
I mean, on one side, I guess we have the AquaWatch ambition that, especially if we end up building satellites, they will have to be public funded by government, and that in my book means we want to make all the data freely openly available to anybody. What happens and how they use the data is something I guess we try to not get involved with. There are some cybersecurity issues, and in the case of the Novasar satellite that I mentioned before, where users effectively can task the satellite and collect data over areas of interest, we have a few more, let's say, filters in front of it. We have a bit of a science review process to understand what they want to use the data for from a scientific perspective, but we also have an assessment that's to do with which country they come from, what are the uses they want to use it for. So there's a bit more rigorous, because again, in that case, they can potentially collect data anywhere in the world, and it could be all sorts of people that perhaps we're not meant to be using that data from our perspective. The first question I got asked the other day when we were launching the facility for Novasar by a certain radio host was, will you be able to see me sunning myself naked in my backyard when you with your satellite? And first question they asked, they always do, how much can you see? And so in this case, of course, Novasar can't see that much detail, but it's really interesting how people really worried that suddenly, we can see people's houses and farms for the last 30 years, but people still think that we can just see so much more detail. At least we can't. Maybe other parts of the government can, but not us.
That's reassuring to know.
Yeah.
Well, I have a question from Jeff in the chat, who has a bit of an issue with some technical issues.
Yeah.
So thank you very, very much for a very interesting presentation. I would be interested to hear a little about potential opportunities for a university such as Monash to collaborate on the program.
I suspect, AquaWatch, I guess, it's primarily, I think Monash might be a member of the SmartSat CRC, so you might already be indirectly already collaborating, but if not, we have this opportunity to develop or set up pilot projects in the different parts of Australia. For instance, Port Phillip Bay might be an interesting place to look at, and begin to think about how would you integrate sensors and satellite data, and how would you use, in fact, even AI on board the satellites, or other ways of processing the data. That's one I think one quick way. And I think there is different opportunities, I guess, for students also and postdocs to be involved, because the CRC is funding those sort of opportunities directly. At a more sort of industrial level, sort of space industry level, we're starting to have conversations with universities around them designing and building new sensors or small CubeSats that might help towards building the technology that we need for Aquawatch in the future. We certainly haven't solved the technology issue yet, again, because of all these trade-offs that we need to try to accommodate between different users. But there is quite a bit of R&D that still has to be done before we can launch a satellite that will be up there for 5 years and monitoring water quality day in, day out. Lots of options. Happy to discuss and follow up later on. Yeah.
Thank you very much, Alex and Jeff. I hope that answered your question. So we have started to reach the end of this seminar. If there's a final burning question, this would be the moment to ask and raise your hand right now. If not, we might all be looking forward to some dinner. That leaves me just last minute to say thank you very much, Alex, for sharing all your valuable and really interesting insights and all the work you do, and also for being open with an invitation for everyone to contact you and to find collaboration.
Yep.
So maybe the last thing to say is that everyone, thank you also in the audience for participating. I think you'll receive a short survey through which we will gather your feedback, and you can also make suggestions for any future speakers you would like to hear in this seminar series. So thank you, everyone, and special thanks to you, Alex.
No problem. Thank you very much. Good night, everyone.
Bye-bye.